Hello, John Furrier with theCUBE here in our East Coast studios at the New York Stock Exchange. Of course, we have our Palo Alto studio connecting tech and Wall Street, Silicon Valley, and money. This is our AI Factory series where we're featuring the leaders who are making it happen. Of course, NVIDIA, the leader in AI and AI factories and AI technology has been making the market. They're the most active stock here on Wall Street. Of course, in Silicon Valley, all the innovators are leaning into NVIDIA. We got Gilad here. He's the Senior Vice President of Networking at NVIDIA, CUBE alumni. Welcome back. Welcome to our first time in our studio here on the East Coast. This is our East Coast access point. It's our Metropod point of presence. Networking, Silicon Valley, and Wall Street. Thanks for coming on.
Happy to be here.
So I want to get into some of the cool things. NVIDIA dominates the boards here in terms of the financial markets, but as people look at the future, there's a lot of roadmap, a lot of things happening in the market that people are learning more and more about. I think of the past 3 years at GTC, you're starting to see very transparent disclosure from NVIDIA. Hey, this is our roadmap. Jensen's very clear what he's doing, supply chain and the ecosystem are developing, but networking is the hottest area. I've been screaming at the top of my lungs on theCUBE, networking is the operating system. Jensen said it. And Dynamo, KV Cache, whatever you want to call it, and networking is the key to success. You are key to that. InfiniBand connecting Blackwells, now you got scale out, scale across. You're seeing a lot more kind of, I won't say convergence, but the collapsing of Spectrum-X. You got connections and interconnects. The key to this factory model in supercomputing and accelerated computing is these interconnects. Right. Describe what is an interconnect, because a lot of people here, certainly on Wall Street, like, I don't understand all this interconnect stuff. Why is it magical? Why is it such an important? Why are people talking about interconnects?
Yeah, so I think it's very simple. Okay, it's really very simple. When you build a data center consists of compute engines and something that will connect those compute engines together. Now, in traditional data centers, or before AI, most of the workloads were just running inside one server, inside one CPU. And therefore, the most important part in the data center was the compute engine itself, and you just needed a capability to access it. So if user wants to run a workload on the cloud, you need a way to access the server, but then the workload just stay within a single CPU, for example, or within a single server. Now, when we look on AI, those are distributed computing workloads, which means it's a workload that cannot be executed just on a single CPU, just on a single GPU, just on a single node. That workload needs to run across multiple GPUs, multiple servers, and we're not talking about 2 or 3, we're talking about thousands and tens of thousands and hundreds of thousands. So now, the compute engine, it's not just a GPU ASIC, but the compute engine is the entire data center. And therefore, you need to have a way to take those GPU ASICs and connect them together so they can exchange information between themselves and to form a single unit of computing out of those ASICs, out of those GPU ASICs. And therefore, you need to bring an interconnect infrastructure that makes that connections. Now, that networking, that interconnect infrastructure, it's not just, I need to move a simple data from one side to another side. Because you need those engines to behave like a single unit. And therefore, you need to build something that has very low latency, something that has ability to move massive amount of data between those compute engines. Everything needs to be synchronized. Because if the two of us are working together to finish a task, if you're going to do your job first, and I'm going to come second, the jobs will take a long time to finish. In order to make it more efficient, we need to work together. We need to be very synchronized in the way that we work. The same goes here. So that connectivity cannot have jitter, which means one GPU cannot get data before another GPU get the data, or one cannot be after the other, because that will delay everything. And this is what networking does. Networking connects compute engines, connects compute ASICs to form a single supercomputer that needs to scale across hundreds of thousands of GPU units.
Yeah, and what I like about that description is it sets the table for why this wave has happened, this accelerated distributed computing paradigm, because the single node was the old model. Hey, put a server in there, load some software, do some stuff on it, whatever. Now you're basically saying, okay, let's take all those computes, make it one single thing, like an entity, like a data center. Now they're talking to each other as if it's one unit. Okay, great. Makes a lot of sense. You network it together. But talk about the role of software, because what all makes this work is now the software, because it's not as simple. There's like many tasks happening. We could be working together, but we have clones of each other, there's other things coming in, contending for resource, and so there's all kinds of complexity that evolves from this new architecture. So okay, put them all together, that makes sense, it's a system architecture, but now you got to overlay software. Talk about that piece of it, because I think that is what's coming out of this wave.
So, at the end of the day, you build a data center to run software. That's the purpose of it. But I don't look on that as separate elements, meaning there is a separate software, there is a separate hardware. When you build a supercomputer, you need to build it in a co-design way.
Yeah.
Okay? Co-design means that what you need to run on the software side, the workloads that need to be executed, the problems that you need to be solved, needs to map into the hardware, the infrastructure that you built. And it goes all the way from the workload, the framework, the libraries, the devices that need to execute, the connectivity, the management, the telemetry that enables you to optimize everything. It's one big co-design of a data center. At the end of the day, of course, you measure that in the outcome. You measure that in tokens per second. You measure that in the productivity of the workers that are running on top of it. But it's not separate element here, separate. It's one co-design that actually enables those AI supercomputers.
2 weeks ago when we met in DC for GTC, and I guess it was kind of a mini pop-up GTC. It was really huge. Jensen used the word extreme co-design. With the word extreme, makes it sound a little more sexy. But talk about the co-design piece, because I think you guys pioneered that one with the way you're thinking about the interconnects, the multiple resources together, compute, and then the co-design piece, you guys pioneered that. And the other trend that you guys also pioneered was density. You know, in the old days, density, whoa, density is too many parts. You get a lot of heat, all kinds of things could blow up. You got the co-design, you got density. Density is actually a feature, not a bug in this, because the more you get closer, talk about that concept of co-design, extreme co-design, and the density opportunity challenge that you guys solved.
Yeah, so co-design, it's the way to build a supercomputer. When you build a supercomputer, everything needs to work as a single element, right? When you build a race car, it's not that I can pick a wheel from that company, I can find another piece from here, and I'm trying to stitch stuff together. That will not give you a race car. A race car needs to be an element that is so optimized in everything that it does in order to be able to win the race.
Yeah.
That's what a supercomputer is. A supercomputer is not a collection of elements. It's a co-design that covers everything from the software to the hardware to build a single unit of computing. Now, density, or the way that you can refer to it as computing density, for example, data center density, is one of the means to build something that is very, very optimized. When you're building an AI supercomputer, it's an expensive unit of computing. And you want to make it the most efficient that you can. It needs to be the most optimized that you can. And when you deep dive into the infrastructure, you have those GPU ASICs, and you have the infrastructure that connects them together. And actually, it's not just a single infrastructure. There are several infrastructures. There is a scale-up infrastructure that connects those GPU ASICs and made them like a rack scale GPU. There's a scale-out infrastructure that connects those racks together to form that supercomputer. There's the scale across, because I would like to connect multiple data centers to make multiple data center a single unit of computing. I have a north-south network, I have a storage network, and I need to have a good storage processor that enables the storage access, especially for inferencing, there is multiple infrastructures in place. And you want each of them to be fully optimized. Now, when we look on a scale-up infrastructure that takes those GPU ASICs and form a rack scale GPU, for example, there is a huge amount of data that needs to go between those GPUs. And therefore, there needs to be a media that actually connects those. And the most effective, the most cost-effective media is copper. Now, copper has limit of distance. And if you can pack, if you can increase the density of those GPU ASICs and use copper, use the most efficient way to connect those. And that's why we're focusing on increasing the density in a rack. That's why we brought liquid cooling. And liquid cooling enables you to put more GPU ASIC in a rack and use copper and actually build a most efficient data center. Now, when you go and connect those racks, then you cannot use copper anymore because of distance. This is where you use optical connections. And in order to increase the efficiency there, if for scale up, we're focusing on density and using copper, on a scale out, we brought co-packaged optics. And we built both Quantum-X InfiniBand with co-packaged optics or Spectrum-X Ethernet photonic with co-packaged optics because that reduces the amount of energy you need to invest in moving data between those racks and building the most efficient infrastructure for scale out.
That's a master class. I really appreciate the commentary. So now we're back to interconnects. Copper, very efficient, good energy savings there. Then an interconnect is, InfiniBand, Spectrum-X, Quantum-X, you got that kind of high throughput, key connections across to other racks. Racks are highly optimized, they do their thing, like you talked about, multiple compute engines and fabrics around that, optimized like a race car, then they connect across. Now, you mentioned co-packaged optics. There's two things that people are talking a lot about now. Jensen put it on a slide at GTC. He had kind of the AI stack. I don't know what he called it, but it was like an AI stack. At the bottom, the physical layer, he had energy. Okay, energy is now like the physical layer. Energy and then latency becomes effective because scale up or scale across, you want to do this in the fastest way possible. So working together, we got to have almost real time, speed of thought kind of latency. Because that's the third scaling law. Talk about that dynamic between energy, savings, latency, because you guys are getting that right. You obviously see it as a physical layer, and that's bounded by energy. Everything's bounded by energy. Talk about those two pieces, because co-packaged optics, optical connections, in my mind, I think, oh, this connecting thing's got a little connector. That could fail. Okay, too many in a rack. Anyone who's done networking cabling knows, okay, I put it in, you do your best job, but it could fail, but does that introduce latency? There's engineering involved. Explain the concept of the energy and the latency when you start thinking about these interconnects like co-packaged optics, like Spectrum-X and others.
So first there is good amount of engineering that goes into building those supercomputers, and I'm happy to work among very smart people at NVIDIA that build those engineering pieces in every place in that supercomputer. It's a privilege to me to work with those great people, really smart people. You're completely right. One of the limiting factors of the capacity of a data center, it's energy. Energy will detect, or energy will set how much compute you can build, you can bring into that data center. Energy will mandate that data center scale. Now, in order to maximize what we have, in order to maximize the energy that I have in a single place, I want to make sure that everything is most energy efficient. That's why copper for NVLink. That's why copper for scale
Copper's
out,
great.
Copper consumes zero power. Now, when we look on scale out, in the traditional data centers, you didn't need to use much of scale out. And therefore there was no much fiber, there was no much optical connections, and the energy that was spent in optical connection was not that critical. When we're talking about scale out on an AI supercomputer, there is a good amount of data that needs to go between those racks on scale out. And therefore there is a good amount of fiber optic connectivity, which means that we're spending a lot of energy there. And you spend the energy because the distance needs to cover by light. So you're moving data over light, photons, but then you need to translate it to electrons in order to connect into the switch, in order to connect into the SuperNIC, and so forth. And this is where you spend energy. Now, we want to minimize that, because today, that energy can almost get to a 10% of compute capacity. So getting 10% more compute in an AI supercomputer, it's really important. And the most efficient way, or the way to minimize energy consumption, is to take those optical engines, those engines that on one side connects to electricity, on the other side goes to light, and drive the signal over distance, to take those optical engines and put them as close as you can to the switches. And if you do that, then you can minimize the energy consumption. Think that I need to talk with you or to convert something, and you kind of sitting far away, I need to spend a lot of energy to reach to you. But if you sit close to me, I can spend the least amount of energy. That's why co-packaged optics. Moving the optical engine to be very close to the switch, for example, and I need to spend much less power, and then I can optimize the scale-out infrastructure.
What does co-packaged optics mean? Because when in the extreme co-design, what I hear you saying is that you're making optics integral to the system, like a race car. What is the key? What does co-packaged optics mean? Is it just embedded into the chips? Describe what it is. What's the...
So let's assume you have a GPU that connects to the NIC. NIC connects to the switch, and then the switches connect to more switches between them. The way that a switch connects to another switch is that you have a box, the switch box. That box has ports, which is interconnect ports. And into that port, you actually plug what we call the transceiver. A transceiver is an entity that has an optical engine, sometimes has a DSP, and has laser sources that actually create those light. And that transceiver will communicate to another transceiver that is plugged to another switch at the end. Now, that transceiver sits outside of the box. And it includes a lot of laser sources. It may include a DSP.
It's like a translator.
And it's an optical engine. And that engine needs to drive the signal all the way into the switch itself and spend a lot of energy in doing that. Because there's a lot of single transitions until it gets into the switch ASIC itself. Co-packaged optics means that we take the optical engine that sits outside of the box and put it in the same package as the switch. So now the light goes all the way to the switch package. And then from that point, it's very close.
You cut a lot of the...
And then you can cut energy. You can save almost 3.5x
on energy
consumption.
What about latency?
Of course, you reduce latency because there is this component that needs to go through. And you also increase the resiliency of the data center, which is very important. You increase the uptime of the workloads. You can increase the runtime, non-interrupted runtime by 5x using co-packaged optics because there is less components. Things are much more reliable, things are much more resilient. It sits inside of the package, so the entire data center becomes much more effective, and we're actually building a better AI data centers with both Spectrum-X Ethernet photonics or with Quantum-X InfiniBand photonics.
Everyone loves to talk about F1. You mentioned racing. Of course, all the tech companies have their logos on these cars. It's like that. You don't want to have a race car with all these off-the-shelf components. Essentially what you're saying is the way optical was before. You have transceiver. That was the state-of-the-art connection point, the interconnect. Now you've embedded it into the switch, so you reduce a lot of that in between.
Right. You make
energy savings,
much closer,
energy savings, reliability, and also speed and latency. So you don't want your car to fail. Some little switch breaks, moving data around. Okay, that's great. Now as you look at the build out, as we saw in GTC, the scaling laws, thinking is the new third power law, scaling law. Jensen presented NVIDIA's vision there. as you look at supercomputing coming up, you got a lot of content around, okay, CapEx build out, everyone's talking about that. Now the next wave is edge. I kind of teased out at the conversations that there's going to be micro factories soon, because distributed computing works in a beautiful way. You know, get the centers down, factories first, hyper-converged edge, maybe a micro factory in between, talking to some satellites, whatever. A lot of networking. Networking is the fundamental future of all AI.
Right.
And you're seeing that with the telecom announcements with Nokia. So I guess my question to you as SVP of networking, the aperture has changed. So you got the scale up, scale out, scale across, co-packaged optics. Now you got a whole nother sphere or realm of networking. What's your vision around some of these things that are emerging? Because the efficiencies with co-packaged optics could be kind of co-packaged factory connections. Because if I have an edge device, why wouldn't I want to bring training and inference at the edge? I mean, well, the Thor development I've been following is highly compelling. That's got to talk to the factory. What's your thinking around that?
Well, and that's another example of co-design. And co-design, it's not just inside the data centers, it's connecting data centers, it's go to the edge, as you mentioned, and how do I get to the edge? It's networking again, right? And I need to make it very efficient. We also introduced, by the way, Bluefield 4. Bluefield 4 is a data processing unit, and it's very key to AI supercomputers. Bluefield 4 sits in several areas. One, it sits as the core of the storage infrastructure because it runs the storage stack. And in inferencing, it's really important to be able to get access to storage and KV cache and a lot of area around storage platform. And that device runs the entire storage infrastructure on it. It sits on the compute server, it sits on the storage sites. It's a great storage processor. It also a security processor because it enables secure access by separating the infrastructure domain from the application domain. And it's a great device for the edge.
Yeah.
Because you need to have more computing at the edge where you place GPUs at the edge, and we actually can have the Bluefield 4 data processing unit to be the compute, the secured access, and actually also storage processor as well.
Yeah, I mean, it's funny, the old days, not to date myself, but you know, storage, compute, networking, they all had their boxes, they'd connect them with some Ethernet, you know, you do some things with it, you go to the storage, make a query, route the packets from point A to point B, process them. Now, networking's actually in the storage fabric too, so you got to talk to storage and memory, so HBM memory. So, you know, it's very clear to me that has collapsed in and with networking software as fundamental. You mentioned edge. I mean, my view is that that's going to hyper-converge with every spectrum and Ethernet, and essentially maybe a AI factory box. Jensen held it in his hand, he said, AI factory in my hand, did a meme on that. And like, why not sister that up against a wireless access point and run full multi-protocol, seamless access with AI embedded into the networking there? Because, I mean, wireless is networking, but they don't have AI. So I see that coming very, very quickly. That makes networking even more critical because that's really scaling across to the edge.
Yeah. So networking, as you said, networking is key. The networking is essentially the heart of the data center. And when you design networking for AI supercomputer, networking for AI at the edge, networking for AI for 5G, 6G, it's not that you just do off-the-shelf element or take off-the-shelf Ethernet and just connect that. You need to carefully design something that enables you 100% synchronization across that entire supercomputer, across multiple supercomputers, across the supercomputer and the edge.
Yeah.
And that's the core element when we designed the Spectrum-X Ethernet. The core element was to make sure there is no jitter, which means there is no skew of synchronizations between those compute engines. You build a full balanced system, you build a supercomputer, everything needs to work fully synchronized as a single unit. Because
Well-
if you have, for example, 100,000 GPU data center, and only one GPU is delayed, all the rest are waiting,
Yeah.
doing nothing and waiting for that single GPU to end. This is why jitter is so critical.
Yeah.
This is why off-the-shelf
Yeah.
Ethernet was not an option for building AI supercomputers, and this is why we created Spectrum-X.
Orchestration, resource management, sounds like an operating system to me.
Yeah.
So, I mean, I think what I love about what you're doing is you're cracking the networking code in a whole nother way, and once OS is, I put that in air quotes, OS as a coordination layer, apps come. I mean, just think about the end user benefits of having AI anywhere from the edge. I could be at a retail outlet. Okay, yeah, I can do facial recognition today. They can do inference. But imagine if I walk into a retail outlet and they say, oh, there's John. He's with Gilad. Oh, they're hanging out together. He's at NVIDIA. He's the CUBE host. Instantly goes back. My agent gets my model, brings it to the edge. Now I'm having a completely different AI-enabled experience that never existed before.
Yeah.
And I could even go, hey, look at my Ring doorbell. Like that, how does that happen? So imagine that kind of intelligence from networking where you can span topologies and handle all that with AI under the covers.
Yeah. Every data center is going to be accelerated. Every element is going to be accelerated. And we need to make sure that we're bringing the co-design technology into every place.
Yeah.
That's why we are working in a large ecosystem.
Yeah.
So the technology that we built is being used by many of our partners and customers to enable AI technology, AI capabilities in every place.
Yeah.
We built Spectrum-X Ethernet
Yeah.
infrastructure that is being used by OCI, that is being used by Microsoft, and they're running their operating system, Sonic, on top of that. It's being used by Meta, and they're running FBOSS operating system on top of that. So it's not just building something that is very synchronized co-design, it has a full flexibility that everyone can run its own operating system on top of that.
Yeah.
The partnership with Cisco, it's a great partnership because we bring the AI capabilities of Spectrum-X Ethernet into the Cisco switches, and then Cisco enables their enterprise management across that entire infrastructure and enable enterprise customers that need that enterprise simplicity to continue having that enterprise simplicity with Cisco.
You guys are bringing core.
But now everything is inside.
You guys are bringing core AI to other people, and co-design is a really pioneering movement. And I think bringing that out in the open with the ecosystem, obviously in the supply chain, clearly that's been working for NVIDIA. But you know, Cisco has AI too. They have some AI action, but you're bringing NVIDIA AI, factory AI, to them to add value to their AI. And I just think it's going to be a great run. I think co-design's genius. The networking is, I think the fun, we're watching it very closely. I think that operating system concept of what networking will continue to do, but morph into a lot of AI inside the NVIDIA system to create value. Thanks for coming on, appreciate your time.
Thank you for having me.
Great to have you, always geeking out here with NVIDIA. Networking is the future of all OS transactions with AI-enabled infrastructure, and AI infrastructure is the hottest area. Beyond the data center AI factories, you're going to have a lot of other AI factory-like systems all talking to each other. They can't be waiting, they're going to be processing. The software's on top, integrated in, co-design as the feature. We're doing our part to co-design content here in theCUBE. I'm John Furrier, your host. Thanks for watching.